Welcome friends. In this video we will be looking at the divergence theorem. Here we will be mainly concerned with evaluation of flux integrals over closed surfaces like spheres that actually enclose a region of space. So in previous videos you might have seen what is a flux integral and what is flux. So here we will be making use of this divergence theorem to evaluate the flux. So here we will show that flux across such surfaces can be expressed in terms of the divergence of the vector field. So first of all, what is divergence? So if you have, say, a vector field like this, F is equal to Fi plus Gj plus Hk, then the divergence of F is defined as dou F by dou x, that is dou by dou x of the first component, plus dou g by dou y, that is dou by dou y of the second component, plus dou h by dou z, that is derivative with respect to z of the third component. Now suppose we are having a solid G whose surface is sigma, okay, and it is oriented in the outward direction. If F is equal to, say, Fi plus Gj plus Hk, and FGH, all of them have continuous first order partial derivatives on some open set containing G, and if n is the outward unit normal on sigma, then the flux integral phi, so this is the most important point here, the flux integral phi is given by double integral over sigma f dot n ds. This flux integral by the divergence theorem is equal to triple integral over G divergence of F dV. Okay, so G is the solid whose outward surface is given by sigma, then the flux through sigma is given by triple integral over G divergence of F dV. This is what the divergence theorem states. Now we will be making use of this divergence theorem to evaluate some questions, some flux integrals in the following questions. So here, this is the written form of the divergence theorem. So usually when you have a surface with the outward orientation, then the flux around such surfaces are called the outward flux. Okay, so the divergence theorem in words can be said as the outward flux of a vector field across a closed surface is equal to the triple integral of the divergence over the region enclosed by the surface. So G is the solid, and suppose sigma is the surface of G, then the flux, the outward flux about sigma, it can be written as a triple integral over the divergence of the vector field F dV. Okay, this is what the divergence theorem states. Now let's look at a question. Use the divergence theorem to find the outward flux of the vector field f of xyz equal to zk. So we have the vector field as f of xyz equal to zk across the sphere x square plus y square plus z square equal to a square, x square plus y square plus z square equal to a square. So first let's write down the divergence theorem. The divergence theorem says that the flux integral double integral over sigma f dot n ds is equal to triple integral over G divergence of f dv. Okay, now f here is, say, 0i plus 0j plus zk. Okay, so divergence of f, so here this is your small f, g and h respectively. So divergence of f will be dou f by dou x is 0 plus dou g by dou y is 0 plus dou z by dou z. So you will be having dou by dou z of z, that is equal to 1. So divergence is 1. So using the flux integral, phi is equal to triple integral over G 1 times dv. Now what is this g? G is the sphere with radius a. So g is the sphere with radius a. Okay, so g is the sphere here with radius a. Now triple integral over g divergence, triple integral over g 1 dv. That means we are actually evaluating the volume of the sphere. When your f is equal to 1, what you are evaluating is the volume of the solid g. Here the solid g is a sphere. So the volume of the sphere, we don't have to substitute the limits and all those things. It is 4 by 3 into pi a cube. Here a is the radius. 4 by 3 pi a cube is the volume of the sphere g. Okay, so here in this question the flux is equal to 4 by 3 into pi a cube. Now let's move on to the second question. Here we have use the divergence theorem to find the outward flux of the vector field. F is given as 2xi. F is equal to 2xi plus 3yj plus 3yj plus z square k plus z square k across the unit cube. So they have given you the unit cube. So unit cube is a cube with sides 1. So okay, so if I'm drawing, suppose this is the cube, so you'll have the unit cube something like this. Okay, this is the unit cube, so all the sides are 1. Okay, now first of all let's evaluate divergence of f. Divergence of f, here your small f is 2x, g is 3y, and z is z square. Sorry, not z, h is z square. H is z square. So dou f by dou x. So divergence of f is dou f by dou x, that is 2, plus dou g by dou y, that is 3, plus dou h by dou z, that is 2z. So you'll be having 5 plus 2z. So the divergence theorem says that the flux across sigma is equal to double integral over sigma f dot n ds, which is equal to triple integral over g divergence of f dv. Okay, that is equal to triple integral over g divergence of f is 5 plus 2z, so 5 plus 2z into dv. Now when we are taking the limits of integration, you see clearly here the limits of z will be z equal to, so the bottom surface, when you are considering the limits of integration, first you have to consider the limits of the bottom surface and top surface of the solid. So the bottom surface and the top surface, the bottom surface is z equal to 0 and the top surface is z equal to 1. Now you have to take the projection of the surface onto the xy plane. So the projection onto the of the surface onto the xy plane is this given region. You see, it is this given region here. Okay, so that is a square with radius 1. Okay, so here if I take a strip like this, this is a rectangular region, so you don't have to take the strip. So it is just, then you will be having y equal to 0 to 1, y limits are 0 to 1, y limits are 0 to 1, and x limits are also 0 to 1, x equal to 0 to 1. Okay, so even if you take a strip like this, it moves from this end to this end point. This extreme end point is x equal to 0, this extreme end point is x equal to 1, and then you have the limits of the y limits as the lower curve and the upper curve. So the strip is traveling through y equal to 0 here, and the strip is traveling through y equal to 1 here. So you'll have it like this, 5 plus 2z into dv. Okay, so the first two integrals is with respect to x and y. So you will have this integral is integral z equal to 0 to 1, integral y equal to 0 to 1, 5 plus 2z into we will have to write this dv as dx dy dz. So with respect to x, we are integrating with respect to x. So 5 plus 2z is a constant, x within the limits 0 to 1, dy dz. So next, x within the limit 0 to 1 is 1, then you will be having z equal to 0 to 1, 5 plus 2z into y. Okay, y within the limits 0 to 1 dz. Again, y within the limit 0 to 1 is also 1, so that term is also 1. So you'll be having this is equal to integral z equal to 0 to 1. Now we can integrate with respect to z, so you'll be having 5z plus 2 into z square by 2. So 2 will get cancelled. This is within the limit 0 to 1. So we'll be having 5z. 5z within the limit 0 to is 5 into 1 plus 1. So you'll be having 5 plus 1, which is equal to 6. So the flux across the surface of the cube is equal to 6. This is using the Green's theorem. You see how easy the Green's theorem is, because otherwise you will have to take all these 6 surfaces and evaluate the flux. So now you are easily able to evaluate flux just as a single triple integral. Now we will move on to one more question here. Use the divergence theorem to find the outward flux of the vector field f of xyz equal to x cube I plus y cube j plus z cube k. So x cube I, f is equal to x cube I plus y cube j plus z square k. It is z square k, yes, plus z square k across the surface of the region that is enclosed by the cylinder x square plus y square equal to 9, and the planes z equal to 0 and z equal to 2. So x square plus y square equal to 9, it is a cylinder like this. X square plus y square equal to 9 means it is of radius 3. Between z equal to 0 and z equal to 2, z equal to 0 and z equal to 2, so you will be having a cylindrical solid like this. So this is the surface A, z equal to 2. This is the surface x, z equal to 0 is the xy plane. Okay, so this is what your solid is. Now you have to use the divergence theorem to find the outward flux of the vector field across the surface of the region that is enclosed by the cylinder and the plane z equal to 0 and z equal to 2. So this is your given solid G. So first let's evaluate divergence of F. Divergence of f is equal to, say this is your small f, g and h respectively. So divergence of f is equal to dou f by dou x, that is 3x square. Dou f by dou x is 3x square. Dou f by dou y is 3y square. Dou f by dou z is 2z. Now the outward flux phi is equal to double integral over sigma f dot n ds, that is equal to triple integral over g divergence of f dv, that is equal to triple integral over g divergence of f is 3x square plus 3y square plus 2z times dv. Okay, now what you have here is you have to write down the limits of integration. So writing down the limits of integration, the bottom surface, the equation of the bottom surface is z equal to 0. This is z equal to 0 and this surface will be z equal to 2, right? Z equal to 0 and z equal to 2. Yes, z equal to 0 and z equal to 2. So the integration will come like this. This is equal to integral z equal to 0 to 2. Now you take the projection of the surface onto the xy plane. So the projection is this given circle that you see here. So the projection is the circle with radius 3. Okay, now you can use the polar coordinates in this case. Okay, so using the polar coordinates, so suppose if I'm taking a strip like this, it is moving from this point to this point. Okay, the strip. Okay, so it is taking a full rotation. So theta, the limits of theta is 0 to 2 pi, and this r is varying from 0 to 3. The radius of the circle is 3, so it is r equal to 0 to 3, and then you will be having 3 into x square plus y square. See, x equal to r cos theta, y equal to r sin theta, so x square plus y square equal to r square. So you will be having 3r square. You see the substitution is x equal to r cos theta, y equal to r sin theta, and then instead of dA you will be having r into dr d theta. Okay, so 3r square plus 2z into, you will be having r dr d theta. Okay, so let's evaluate this integral now. So you will be having, this is equal to z limits are 0 to 2, then theta equal to 0 to 2 pi, then you are having r equal to 0 to 3. Let's multiply that r inside, so you'll be having 3r cube plus 2z into r, and then sorry, there is one more term dz here, so dr d theta dz. Okay, so that is z equal to 0 to 2, theta equal to 0 to 2 pi, then you will be having 3r cube. The integral is 3 into r raised to 4 by 4 plus 2z into r raised to 2 by 2 within the limits r equal to 0 to 3 d theta dz. Okay, so you'll be having z equal to 0 to 2, then theta equal to 0 to 2 pi 3 by 4 into r raised to 4, 81 minus 2 will get cancelled, so z into r square is 9, and then you will be having d theta dz. Now there is no theta term here, so integral is just theta. Integral of 1 d theta is theta, so z equal to 0 to 2, then you will be having 81 into 3, 243 by 4 minus 9z times theta within the limits 0 to 2 pi dz. Okay, so the next term will be theta within the limit 0 to 2 pi is 2 pi. Okay, so 2 pi I'll keep it outside into integral with respect to z. Integral with respect to z is 243 by 4, 243 by 4 into z minus 9 into z square by 2 within the limits 0 to 2. 0 to 2. So let's see what is the final answer. 2 pi into z within the limit 0 to 2 is 2. So 243 by 2. 1 2 will get cancelled. Okay, 2 by 4 is 1 by 2 minus 9 into z square by 2. So 9 1 2 will get cancelled. So 9 into 2 is 18. So you will be left with this is equal to pi into you'll be having 243. It's not minus, it is plus here. 243 plus 9z. Okay, so I've written minus everywhere here, so just correct it. That is plus 9z. It is plus 9z, so it's coming out like this, plus 9z plus 9z. So 243, then you'll be having plus 2 yes, plus 2 into 18, 36. So that comes out as 9, then 279 pi. So this is the final answer. So the flux across sigma is 279 pi. Now, so that is the final answer, 279 pi. Now we will move on to the last topic of this video, that is sources and sinks. You see, in an incompressible fluid, points P naught at which divergence of f of P naught is greater than 0 are called sources, and points P naught at which divergence of f of P naught is less than 0 are called sinks. Fluid enters the flow at a source and drains out at the sink. In an incompressible fluid without sources or sinks, we must have divergence of f of P equal to 0 at every point. So this should be very clear to you. See, if divergence at f of some point, say P naught is greater than 0, then we are having sources. Okay, if divergence of f of P naught is less than 0, then we are having sinks. Okay, and altogether, if divergence of f of P is equal to 0 for all P, then we say that it is free of sources and sinks. Then we say that it is free of sources and sinks. Now what happens is, at sources, fluid enters the given medium. Okay, so what happens is, for example, if you are having, say, melting of ice, then what happens is that melting of ice increases the fluid flow, so that will give rise to a source. Now sink means, suppose we are having evaporation of a given fluid, then the fluid flow decreases, so that gives rise to sinks. Okay, so this is what is the difference between a source and a sink. Now we will do one question here. Determine whether the vector field f equal to xyi. So you are having f equal to xyi. F is equal to xyi plus, oh, sorry, minus 2xyj. So minus 2xyj minus 2xyj plus y square k plus y square k is free of sources and sinks. If not, locate them. So we will first find the divergence of f. So divergence of f is, so your small f is xy, g is minus 2xy, h is y square. So dou f by dou x is y, and dou g by dou y is minus 2x, dou h by dou z is 0. Okay, so your divergence of f is y minus 2x. So you will have a source of divergence of f is greater than 0. So divergence f is greater than 0. So source, you will have a source of divergence of f is greater than 0. So divergence of f greater than 0 implies y minus 2x is greater than 0. That implies y is greater than 2x. So at all these, at this region where y is greater than 2x, you will have source. And similarly, if divergence of f is less than 0, then you will have sink. So sinks are at the points where divergence of f is less than 0. That is y minus 2x is less than 0. That implies y is less than 2x. So at all points where y is less than 2x, you will have sinks. So this is the classification. So it is not free of sources and sinks. So the thing is, where y is greater than 2x, you will be having sources, and where y is less than 2x, you will be having sinks. Okay, so this was the last topic of this video. Thank you.